Today, I want to concentrate on the stuff in Unit 11. If you remember, the main theme was analytic continuation. And we'll look at a couple of problems that really need analytic continuation before you can understand what they're all about. After that, we'll lead on to the idea of a Riemann surface, like this one. But before we do that, let's look at a concrete example, something really quite practical. Now, I'd like you to imagine that we give this differential equation to 3 different people, and they come back with their solutions. Now, the first man might come back with a solution in series. Z maps to 1 plus Z squared, and so on. Now, of course, there'll be a restriction on the values of Z that he can choose, because we need mod Z less than 1 in order for the series to converge. Now, the second man might come back with a solution like this. Integral from 0 to infinity of e to the t z minus 1 dt. I wouldn't know how anyone would get a solution like that, but let's suppose he does, and it does work actually. Now, for this case, you need the real part of z less than 1, otherwise the integral won't converge. The last man, well, perhaps he's cleverer than most and comes back with the simplest looking solution. Z maps to 1 over 1 minus z, but even he has a restriction on the values of z because he needs z not equal to 1. Now, those solutions look very different, but in fact they must be in a sense the same because they're solutions of the same differential equation. The question is really, in what sense are they the same? Well, before we can investigate that, we'll have to introduce an analytic idea, the idea of a function element. Now, in our case, we have 3 candidates. That's the notation. The first function was actually this series. The region on which it makes sense is the interior of the unit circle. The second candidate was that integral with the region to the left of the line real part of z equals 1. And the third candidate, 1 over 1 minus z. The region here was the whole plane except the single point z equals 1. Now, all 3 are function elements. They're clearly not the same, but these function elements arise as solutions of the same problem, and in some sense they must be equivalent. Well, it's really all a question of the regions involved, and let's put that in a more general context and look at the general ideas of analytic continuation. Now, here are our 3 function elements, and the essential thing is that in the regions in which they overlap, these function elements are the same, they're equal. And that's really at the heart of analytic continuation. Now, at the top here, you see, we have the general sort of diagram that you find in the text. Here, a function element fr, and its region overlaps with a function element gs. Now, if they're equal on an open subset of this overlapping region, then we say that f and g are direct analytic continuations of each other. Of course, you can have more than one. You can have a whole chain of them. And we call this sort of chain a chain of function elements. Now, in fact, this sort of chain defines an equivalence relation, because if you have a function element fr and a function element ht, which are connected by a chain, then that's an equivalence relation. And there are corresponding equivalence classes. In this particular example, we've got 3 elements of the equivalence class. In fact, we call them analytic multifunctions. These are elements of the same analytic multifunction. But you see, the important thing here is that when you do analytic continuation like this, out from one function element to the next, you carry a property with you. In this case, you carry the property of being a solution of the original differential equation. And that's important because if you've got a series solution like this, if you can check that this is an analytic continuation, say, then you know immediately that that thing must also be a solution of the differential equation. Well, that's one important application of analytic continuation, but there are others. In fact, I don't think you can really appreciate the power of the method until you see us actually build an analytic function, a complete analytic function. Now, a good example of that is the gamma function. Now, we start by defining the gamma function as an integral. This, then, is a function element. It's a function element, and it's convergent, the integral is convergent in this plane above the point 1. But now you see, would it be a reasonable question to ask, is there a value of the gamma function out here somewhere? Well, that only makes sense, of course, if we can continue analytically like this, out into this region. But before we do that, it's very important that we ensure that this function, defined by an integral of that kind, is actually analytic in the region we've been talking about. So our first task is to show that this function element is analytic outside this region. So let's look at the details of that and see how it's proved. Now, the first step is to break the integral itself into smaller parts to form a sum of integrals, each over a finite interval. The general term in the series we'll call Pnz. Now, immediately, there are two objectives for the analysis. First, to show that Pn of z is analytic, and then, if so, show that the series is uniformly convergent. To show Pnz is analytic, you need theorem 5 in unit 11. The theorem uses omega, but in this problem, the variable is t. There are three parts to the theorem. Keeping z fixed, is this function continuous? And now keeping t fixed, is this one analytic? And finally, is the expression in terms of both x and t bounded? Well, first, if only t varies, the function is the product of two continuous functions, and therefore continuous. If only z varies, then that's a known analytic function. But how do you show the integrand bounded? Well, remember, t lies anywhere between n and n plus 1. That's okay, but z can be any number whose real part is greater than 1. The trick here is to only consider those z's with real parts less than some arbitrary number alpha. And that gives a band whose width can be as large as you please. So, you've got to look for a bound for this modulus. By trying the extremes for t and z, you'll find it's not too difficult to come up with an inequality, and so get an expression for the bound on the integrand. And this bound is going to come in later, so let's store it. But at least you see it's answered the question. With z and t in the regions here, the expression is bounded. Well, that completes the theorem 5 part of the problem. We've got bounded integrand, analytic as a function of z, continuous as a function of t, and so Pn of z is in fact analytic. The remaining step, then, is to show that the series is uniformly convergent. For that, you must take the modulus of each term and try to find some bound for the general term. With the estimation theorem, it boils down to finding a suitable m and l. L, the length of the interval from n to n plus 1, is just 1, and that gives m times 1. Now, what about m? That's where that bound on the integrand left over from theorem 5 comes in. With this bound, you can get straight on with the m test for convergence. Now, of course, you need a convenient convergent series, and what better series to choose than the series of upper bounds? But is it convergent? Well, you can apply the ratio test. Use the general term, and you're there. But now, you can apply the m test to test the series of Pn of z's, using the convergent series of upper bounds, and that will prove that the series of Pn z's is uniformly convergent. Well, I hope you understood the details of that proof. If not, you can read it again in the text after the program. You remember that in that proof, we mentioned alpha. It was chosen to be a real number greater than 1, and we showed that the function gamma was analytic between 1 and alpha. But of course, alpha could be as large as we please, which means, in fact, that this function element is, in fact, analytic to the right of 1. Now back to the analytic continuation. Remember, I want to analytically continue out to the right here, out to the left here. Well, it's rather similar to this problem I had before, but you see, here I only had to check that the function elements were equal in the region of overlap. Now I've got a more difficult problem, because I haven't even got the function elements. I've got to construct those before I can check that they are indeed analytic continuations. So let's go on then to have a look at how this construction can be done. I'm afraid there's nothing for it. You just have to roll your sleeves up and do it. Right, how do we start then? Well, we have this function gamma z, this function element, defined as an integral from 0 to infinity of t to the z minus 1 e to the minus t dt. And for what values of z is it valid? Well, for the real part of z greater than 1. That is a region like this. There's the point 1. It's valid in a half plane. Now I want to be very careful about the function elements that I'm talking about. So I'm going to call this one gamma 1. That's the function element gamma 1. Now the trick that you use is to do integration by parts on this thing. It isn't difficult, and if you do it, you find that you get 1 over z, the integral from 0 to infinity, t to the z, e to the minus t dt. I won't do the details, but believe me, that's what you get. Now notice that here you've got exactly the same integral as you started with, except that z minus 1 has become z. So this is just the same thing as 1 over z gamma 1 of 1 plus z. Now what does that mean? Well, suppose that you know gamma 1 of 1 plus z, then immediately you can calculate gamma 1 of z. So that if you have a value here for gamma 1, then you can actually use that value to determine the value of gamma 1 at a point 1 down to the left. And you could do it again, using this value to determine this value, say. But now here's a point. What about doing this? You see, taking a step to the left, but outside the original region of definition of gamma 1. Well, I can't do that until I've got a function element. Well, let's define one then. Let's define gamma 2 to be the function element which takes z and puts it into 1 over z gamma 1, 1 plus z. Now, where does that function element make sense? Well, it makes sense if the real part of 1 plus z is bigger than 1. In other words, the real part of z bigger than 0. So this means that this function element defined this way, it's equal to the previous function element to the right of 1, but it actually takes us out into a bigger region in this stepwise fashion. Now, there's no reason why I have to stop there. I could do precisely the same thing again and step one step to the left again. And I do it by defining another function element, gamma 3, say, maps z into gamma 2, 1 over z, gamma 2 at 1 plus z. And this gives me a function element which is defined in the region up as far as minus 1. And I can keep on doing this. I can keep defining function elements taking me further and further and further to the left. Now there's only one slight difficulty, and it's this, that in here, you see, we've got 1 over z gamma 2 of 1 plus z, so that the point z equals 0 is obviously going to cause us a problem. And similarly, when we take a step to the left from that point, we're going to have a problem there as well. The function isn't going to be defined, in fact, at any of the points on the negative integers or at 0. Well, let's see how that discussion fits in with what I was saying earlier. Here, you see, we've taken steps to the left, and we've got analytic continuation by steps in this sort of fashion, over and over from one region to the next. It's like this process here, except that instead of, in this case, when we were talking about the differential equation, the analytic continuation carried the property of being a solution of the differential equation with it. That was the important thing. Here, It's the actual property which enables us to do the analytic continuation. It's this property which is crucial. That's the thing which enables us to do it. But there's another thing I'd like to point out about these two solutions. In the first case, this man here had a solution of the differential equation which applied everywhere except at 1. And in a sense, he's got the best possible solution. That domain couldn't be improved. In this analytic multifunction, there is a function element with the largest domain, in other words. Is it true that there's a function element in this analytic multifunction with the largest domain? Well, there is, but I haven't yet found it. I found lots of function elements, it's true, but I haven't yet found the function element with the largest domain. Now, I'll leave it to you after the program to see if you can actually formulate this function element. I'll tell you there is one, but you've got to find it. Well, that raises quite an interesting question about analytic continuation. Is there something about analytic continuation which means that there's always going to be a function element with the largest domain? Well, in fact, there isn't. And you don't have to look very far to find an example. The log function is a good counterexample of that property. Let's start then by supposing that there was a function element for log which did have the largest domain. Let's have log then. What would that largest domain look like? Well, I think it's pretty clear that it would have to be the whole complex plane with the origin removed. How do you calculate log? Well, you write down log of z is equal to log of mod z plus I theta. And the only problem is in determining theta. Now let's start with a function element like this, a function element which has that sort of region as its domain. In other words, theta is somewhere between 0 and pi. Now the values in there are precisely determined because this region is a subset of this largest domain region, this largest region that we started with, and so we know exactly what the values, supposedly, the values of log ought to be in there. Now let's do some analytic continuation. Let's arrange for a function element to be exactly equal to this function element in this overlapping region. And to do that, the theta that we choose has got to have the property that it lies greater than pi over 2 and less than pi, 3 pi over 2. Now do it again. This time, in order to make the analytic continuation work, we've got to have the theta greater than pi and less than 2 pi. Now you can see that I'm gradually working my way round till I get back to where I started from. In this function element, then we've got to have theta greater than 3 pi over 2 and less than 5 pi over 2. Now finally we get back to the original set, and now what theta have we got to choose? Well, in order to do the analytic continuation from this region to this, we've got to have theta being greater than pi and less than 3 pi. But you see, that gives us different function values from the first region to this last region, and that's a contradiction. So there can't possibly be a function element of log with the largest domain. Now, there's a way of resolving this particular problem with log. You see, what it means is that you can't regard log as a function. That's the basic problem. You have to consider a multifunction, lots and lots of functions. Now, you can get out of that by saying, well, look, I won't allow this last region to be actually equal to the first region. Somehow it's different. How is it different? Well, somehow it's not in the same place, as it were. So what I'm suggesting is really rather odd. I'm suggesting that we should, at this stage of the game, effectively throw away the complex plane and look at functions defined on some other region than the complex plane. And this is the idea that leads us to a Riemann surface. Well, this nice thing is the Riemann surface for log, and not all of it, the essential part of it, the spiral part of it. Now, we've built it on top of this base, which represents the complex plane. There's the x-axis, and over here, the y-axis. Now, the essential point of a Riemann surface like this is that it gives you more information. It tells you not only which point z, which complex number z you're talking about, but it also tells you which theta to associate with it. Now, let me show you how that works. Have a look from above. Look down on this thing, and I'll put in a point. Now, there's a point. Now you tell me, you can tell me what complex number that is, but tell me what angle it's associated with. You see, you've got no idea. But if you look from the side, now, look from the side, and you see that it's at that height, going round once like this. So you go round once, and I've gone round up through 2 pi. So that height that I've gone up tells me the angle to associate with this point, and in fact the angle I know has now got to be 2 pi. So that's the sort of extra information I get from a Riemann surface of this kind. Now let's see how it works out with the log function I was talking about before, with the elements of log that I had to start with. Here then is the first element, between 0 and pi. The second one, we're doing analytic continuation now, not on the complex plane, but on the Riemann surface. That's the next function element. Now the third fits on like that. And the fourth. There we are. Now, the crucial step, of course, is to put the last set in. And just so that you can see this more clearly, let's put the lights down a bit. Now, here's the last set going in. See, right over the top of the previous one. Now, those two sets, to you looking down on it, look exactly the same sort of complex numbers. But in fact, those sets are on the Riemann surface. So they're different sets, and that gives us good reason for believing that they should give different function values on those two sets. They're different function elements. So this is the beauty of looking at the Riemann surface for log. You can distinguish one function element from another, and what's more, now we have the possibility of a function element of log with the largest region. In fact, the largest region is the Riemann surface. So essentially then, with log, you've got a choice. You either stick to the complex plane, in which you have an analytic multifunction and all its function elements, or you go onto the Riemann surface, in which case you have one function element that will do the job for you, and you have all the simplicity that that entails. So it's a choice. It's up to you, really. Now, I must say, I couldn't resist the temptation of showing you a more complicated Riemann surface, so have a look at this one over here. Now, it's actually the Riemann surface for log z minus log z minus 1. And you can see that it's composed of two spirals, one above the origin going around this way, and the other above the point 1 going up in the other direction. And let me turn it round so that you can have a better look at it. You can see quite distinctly the two spirals, which are joined together in the middle by a sort of bridge. There we are. Of course, this is only part of the Riemann surface, but it is the essential part of it. There, now that's the Riemann surface for log z minus log z minus 1. Now, what can you do with a Riemann surface like this that you couldn't do otherwise? Well, let's look at this example. Suppose I asked you to integrate this function around a contour like this. Now, could you see immediately that the integrals along this straight line cancel out with this straight line if this was drawn in the complex plane? There's the origin, there's 1. Well, you can't see immediately, I don't think, but you can if you do it on the Riemann surface. There's one straight line, round on the Riemann surface, down along, round on the Riemann surface again, and up. And you can see that the two straight lines are on entirely different parts of the Riemann surface, and so there's no reason at all why these integrals should cancel out. So that, then, is our more complicated Riemann surface. Now, on the radio this time, I'll be trying to help you with another aspect of Unit 11, the stuff on uniform convergence. But today, I hope we've given you some insight into what analytic continuation is all about.